Full disclosure, I'm an experimentalist who values computation. That's my first qualifier. You all will quickly lose me in your field if you take me too far. But what I thought it would be interesting to do is we're thinking very deeply at Argonne, and quite frankly, a few of the other labs are also thinking about it, and we have been for a while. But you'll see, hopefully, a theme start to emerge as I talk about the lab. How computing, computational science and engineering, and enabling computer science, applied math, and all the things that go with that, modeling and simulation, how that threads through what we're trying to accomplish as a laboratory, and a set of laboratories, and in the national interest. So I'm assuming a fairly uneven understanding of the national labs and Argonne specifically. So for those who know the labs and Argonne specifically better than others, some of this you'll probably be this will be old news. But anyway, I thought I would give you a sense of that. I've got a lot of science examples in here. I don't intend to dive in on them, in part because it's not my work. I know them enough. I know enough but if you take me too deep, I will probably refer you to the papers and such. But I understand how they fit in the broader context and the power of computation as we try to implement our strategy. So let me start with what Argonne does. So you may know, and I'll get to this in the next slide, there's 17 Department of Energy national laboratories, if you didn't know that. And we're arrayed across the Department of Energy, basically working for different parts of the department. So we're one of 10 Office of Science laboratories in the complex. Of course, there's three labs that work through NNSA, that being Sandia, Livermore, and Los Alamos. Again, we're one of 10 Office of Science labs. We, of course, operate one of 2 open science computing machines for the complex, one being Argonne, the other being at Oak Ridge National Laboratory, as well as Lawrence Berkeley has a strong role as well. But the important thing about us, even though we are an Office of Science lab, what you'll see as I go through is we really have a wide range of capabilities. We're so-called multi-purpose labs. So the lab allows us to bring science and engineering to bear on really big problems. And so, as you'll see, I'll go through, I'm going to talk a little bit about more basic science, fundamental science, because that is a core part of our mission, but we really build on that fundamental science base to solve what I would consider very applied problems around, say, energy and national security. So again, here's the map. This is the DOE complex. We're actually a little bit east of Fermi, not a little bit south and west of Fermi, so that's not totally accurate. I should also say that we as a laboratory, each of these labs with the exception of one, that being National Energy Technology Laboratory, are what we would call GOCOs, government-owned, contractor-operated. So we're managed by a contractor. In our case, that's the University of Chicago. It has been since our inception in 1946. The University of Chicago also manages Fermi. Other labs are managed by other entities like the University of California. Stanford manages a lab. There's a nonprofit out of Columbus called Battelle that manages a large, about 6 labs actually. So these contractors are responsible to the DOE to manage the lab's day-to-day operation, responsible for strategy, et cetera, et cetera. Again, wide range of capabilities. There's, again, 17 of us, and you can see the color code just tells you which part of the department they quote their landlord sits in, but again, that does not necessarily reflect the funding. I won't go through all the labs and the scale of their funding, but just to give you all a sense for how we're funded, we're about $800 million operating, which puts us roughly, probably sort of mid-range in terms of the national labs, in terms of budget size. About 60% of our funding comes from the Office of Science, so a very strong footprint of basic science in the laboratory. But more importantly, that other 40% is applied work coming from a variety of places, including the applied parts of DOE as well as industry and other federal agencies. So a very diverse portfolio. And a lot of the other labs can say the same thing. So one of the things that's interesting actually that's popping up now for us, but actually with the change in administration in Washington with Secretary Moniz coming in to be the Secretary of Energy now, he's actually engaging the laboratories, we think, in a much more meaningful way, which is interesting. Of course, Steve Chu, the previous secretary, was a former lab director. He'd done a lot of things, Nobel Prizes and other things, but he was also a former lab director. But interestingly enough, this new secretary, Secretary Moniz, who comes from MIT, I was in DOE, went back to MIT, and has now come back. He's on PCAST. He's very credentialed. He's actually engaging us in a very interesting way as a set of labs. But he's also thinking about the labs as part of their region. And so one of the things that you'll note about that previous map is some of the labs, many of the labs sit in what I would call relatively they're the only game in town. Let's take Idaho. They're in Idaho Falls. They're the largest employer. They're like nearly the largest employer in the whole state of Idaho. Argonne's really different, right? We sit in Chicago, so it's an interesting discussion about how our lab, which sits, by the way, in the suburbs, it doesn't sit in the city. How does it fit? So we've been expending a lot of time and energy thinking about how we fit into that. I'll call it that. Not only this Chicagoland area, but also the Midwest ecosystem. And you can see there's a lot of things around us that we can partner with and leverage. And so we're actively, these aren't just cartoons, we're actively thinking about how we, as sort of the center of this, can reach out tentacles and engage these different industries, other universities, et cetera. We have an advantage that, although we're managed by the University of Chicago, which provides tremendous strength in terms of the intellectual strength of the university, the ability to have joint appointments, and all that goes with that. But we also have very strong partnerships with Northwestern and the University of Illinois through their role all the way up to members of our board. So those relationships become very deep intellectually as well. And then the industry piece, industry through our computing resource, industry through our hard X-ray advanced photon source, and I'll talk briefly about that. So I guess the point being that I think you're going to see more and more of the labs thinking about how they fit into this regional ecosystem, but also more and more how the labs can better fit into this ecosystem of universities and industry. What can the labs bring that's unique and different to really drive innovation in the US? Our mission in a slide, I won't go into details, but along the top, I'll talk a little bit more about pieces of this, but being able to take our ability to take very high energy X-rays to interrogate materials, all the way out to thinking about materials in chemistry and physics at a very fundamental level, using computing as central really to enabling a lot of our work, all the way out to being able to take materials, for example, and scale them up, make a material in say, a vial or a beaker, and scale it up to something in a barrel so that we can then engage industry on how to manufacture it. So there's a tremendous capability there. Those enabling capabilities, so if you ask the 17 labs, where are you different? Some people would look at them and say they're all the same. Well, if you peel the layer of the onion just a little bit, we are different. So some of our enabling capabilities are world-leading and really differentiating. But when you talk about the applied or use-inspired outcomes that we're going after, this is where you can really draw some distinctions. So batteries, I'll talk more about that. For those who know the DOE space, we just won, within the last 6 months, one of these energy innovation hubs. We're the lead organization for the battery storage hub. And I'll talk a bit more about that. It's a large team, but we're the lead organization. Sustainable transportation, I'll talk a little bit more about that. Nuclear energy, so I should have started with, coming out of the Manhattan Project, the core of the labs were created for different reasons. We were created to be the place to develop nuclear energy for peaceful uses. So if you look at the nuclear reactor fleet that's out there, now a couple have shut down, so you're talking about 102 reactors that are currently operating. You can trace that back to Argonne designs. So we were seminal in that. But it's interesting, we've grown from that into this large multi-purpose lab, but we still have a strong core that thinks about what's next for nuclear energy, and I'll talk a little bit about that, and also takes those capabilities and applies it to things around national security, particularly non-proliferation and reactor safety worldwide, and et cetera, et cetera. And then finally, an area that actually is organizationally within the area that Paul and Rick Stevens and Pete Beckman, and names you know, and Rob, they all fit in, a focus on biological and environmental systems, from fundamental biology all the way up to thinking about how one links biology and climate to think about climate change, adaptation, mitigation, the whole shooting match. One of the things that many of the labs do, that the Office of Science labs in particular do for the nation and the world, is we operate user facilities. So you're familiar, right? There's an advanced leadership computing facility that we operate for the department and for the scientific community. We also operate one of the world's top synchrotrons for hard X-rays, very high energy X-rays. And that's actually in the midst of an upgrade. So if you think about our priorities, these are really two very big priorities in terms of keeping these facilities at the cutting edge. But not only that, also our priorities are to have our own folks and working with the community do some really cutting edge science using those machines. And I'll talk a bit more about that. We operate a linear accelerator for heavy isotope acceleration for the nuclear physics community. We have one of 5 nanocenters that is actually co-located on the advanced photon source ring that's operated, that's really, really focused, as the name says, on on synthesis and characterization of nanomaterials for a wide range of applications. And then finally, an electron microscopy center. But again, one of the things that distinguishes the Office of Science labs in particular is our ability to continue to build and operate these cutting-edge facilities. So what about the Advanced Photon Source? It's a very powerful machine. It's got about 5,000 users per year. It's oversubscribed by several factors. Many cool things that go on there. Interestingly enough, about 40% of the use is actually by I'll call it the biology community, to do in a lot of cases, protein structures. So the pharma industry uses it quite extensively to do combinatorial sort of structural analysis for protein structures, ultimately to do drug design. And there's other things like important things like Nobel Prizes that come out of membrane protein structures for this G receptor, protein G receptor in 2012 was because of using our light source as well as a couple of the other light sources across the community. So one of our goals is we're doing a pretty good job of getting Nobel Prizes for these light sources in chemistry, and we need a couple in physics. So we're looking to try to push that into the harder materials area. But this again is a very powerful. It's in the midst of an upgrade. Interestingly enough, this is an interesting place where big data comes to play. We're generating huge amounts of data. When you talk about imaging with these machines, the amount of data that you're creating is humongous. So one of the things that we're doing internal to the lab is thinking very deeply about how we can bring our computing folks together with the folks who generate this large data to really try to think about how to put together the frameworks and the necessary analytics, et cetera, to be able to understand that data, mine it, image it, visualize it, et cetera, et cetera. Of course, you know Mira. This is a picture of the newest the Blue Gene Q at Argonne. It's ordered 10 petaflop machine at the laboratory, just now starting up. And of course, just like Oak Ridge and Los Alamos, Livermore, and Sandia, we're thinking about what's next as well. So we're actively operating this machine for the community, doing really cool science, but also thinking about, okay, let's continue to build this resource for the community. So what happens in 2016, 2017? What happens in 2020, 22? Fifth fastest computer, right? So you guys know this better than I. It started out third, and then now it's fifth. But it's very green. So it's an IBM. It's a Blue Gene series computer, so very green. This is a water-cooled machine. Very, very, very interesting. So what about HPC? This is one example, but really, I think I've really sensed to me that really over the past few years, it's really hitting home the incredible value of computing in terms of driving science forward. This is one example of where HPCs come to play in the more fundamental realm. This happens to be cosmology. This is a simulation on the lower right from one of our scientists and his team, Salman Habib at Argonne. It's basically simulating the early part of the universe and the later part of the universe, showing how things start to become more clumped. And with time, and sort of starts to address this whole issue of dark energy, dark matter, and the evolution of the universe. The important thing also to point out, this requires tremendous computing speed, sort of trillion points kind of level, cranking through pretty fundamental physics equations. But when you start comparing that to observational data like we get from the South Pole Telescope, like we'll ultimately get from the LSST, you're talking about huge data sets that can then be brought together to not only to validate these simulations, but also can be mined and thought about and visualized, and that requires this kind of compute resources. So we and a few other labs are actively working in this more fundamental physics area, again going after things like cosmology, evolution of the universe, but also going after nuclear structure calculations, understanding nucleosynthesis and origin of the elements and things like that. Just another example, I've already touched on this, but this gives you an example as you think about sky surveys, again staying on cosmology or astronomy, starting from very early surveys all the way up to the LSST once it's up and completely operational in Chile. The amount of data that you're dealing with as you're doing a survey of the sky is just going through the roof. And so the importance of being able to couple the cosmologists with this high-performance computing capability is very, very important. And the department's actually probably uniquely qualified to be the right place to bring that together. So we've got a unique suite of facilities. This just happens to be, this is now a picture of the physics accelerator, our heavy ion accelerator that we use again for fundamental nuclear physics work, primarily medium energy physics work. But we can also use this to do a wide range of problems. We're collaborating with in the superconducting area, trying to look at generation using heavy ion bombardment to make interesting new materials that might be able to be used for superconductors. And so one of the things the labs can do is bring these wide range of disciplines together to solve bigger problems. You have to work it with the universities, but really the labs sort of fit that unique. So sort of transferring the talk now a little bit into some of the, I'll call it the more applied outcomes that we're focused on personally. This happens to be a simulation of an experiment of a nuclear, it's basically a simulation of an experiment looking at nuclear reactor type designs. So this is basically coolant flow into the upper plenum of a nuclear reactor, the velocity field of the coolant. But these are sort of thermal hydraulics calculations, but one of the things that we're doing, Oak Ridge is also doing a lot of this, is taking the thermal hydraulics in a reactor, coupling it with neutronics, and then with thermal mechanics, and being able to solve those coupled problems is really, really important to thinking about advanced designs. And so we're actively doing that with computing and using experiments to validate those simulations. So what about batteries? So it's an interesting story, our battery program. It started with, our focus has been primarily up to this point on lithium-ion batteries, so really focused on developing lithium-ion batteries for transportation applications. And I want to sort of tell you a little bit of a story about how we've got from there to where we are today. We started with Office of Science funding, developed some interesting cathode materials, lithium manganese cobalt type materials. Actually, interestingly enough, that started about 12 years ago, and now our cathode material is actually licensed to GM, LG Chem, and it's in the Volt. So that's a great story. It took us 12 years to go from there to there, and it wasn't planned. We didn't start out there thinking we were going to put this into a car. It transitioned from Office of Science funding to EERE funding, ultimately to a license. So one of the questions you have to ask is there a way to sort of think about the path and pace of innovation to go from there to there in a different way? And also, by the way, a lithium-ion battery will take that car. Does anybody own a Volt? I'm going to buy one, I think. It's 40 miles to a charge. So you've got range anxiety and all kinds of other challenges. So how do you think about a battery that could take a car 100 miles on a charge, 200, even 300 miles on a charge? So that brings us to the hub. So that's the acronym. It's the Joint Center for Energy Storage Research. 14 partners. I won't list them all, but I'll make an important point for this for my colleagues at the labs. It's ourselves and 4 other labs: Berkeley Lab, SLAC, Pacific Northwest, and Sandia National Lab are on the team. Universities primarily in the Midwest, University of Chicago being one, Northwestern being another, Illinois as well. But importantly, industry. We've brought industry to the table to help think about how to innovate materials for next generation batteries. So here we're thinking about beyond lithium ion. Again, how do I think about a battery that can take something and drive a car, say, several hundred miles, a few hundred miles? And also, how can I think about integrating renewables onto the grid, and what kind of storage do I need to go do that? So we're innovating in that space, and I'll get to a little bit about computing is a very, very important part of what we're trying to accomplish there. This is animated. But just to give you a sense of what we're trying to accomplish, it's really starting with fundamental cross-cutting science. We're exploring concepts for storing charge in 3 different spaces. One being, imagine you could make a magnesium battery, something doubly charged, or an aluminum battery, say triply charged, rather than lithium battery, which is single charged. Store that much more energy. What if you could think about, instead of lithium ion, think about a lithium air system, where you're storing energy in chemical bonds, and that would be very powerful. Or think about redox type, flow type systems, either for transportation or for the grid. These will allow us, the tagline we use is 5-5-5. So 5 times the energy density, 1/5 the cost in 5 years. If you know batteries, you'll say that's nuts. And it actually is probably unobtainium, I like to say. But it drives the right behavior, because it causes people to really think very deeply about the science. But also the interesting thing is we have this back and forth. Again, I said industry. We've got Dow Chemical, Johnson Controls, and Applied Materials working with us so that we're able to do a really fascinating sort of back and forth between the science and the engineering and back, break prototypes, learn from that, go back and forth, and hopefully be able to design really truly transformational materials and technologies. How do we do it? This is just a plug for the Energy Frontier Research Centers. I won't dwell on this. But part of the enabling science is being able to think about, say, how to design materials that can actually be preferential catalysts. This would have applications in chemical transformation type batteries, but also more importantly, just in catalysis in general. These Energy Frontier Research Centers, we run 2 of the 46 in the complex that the Office of Science has funded. We also have one in energy storage. One of the interesting pieces of science that's come out of that is the notion of having self-healing materials. So these beads actually will break apart at a certain temperature and basically stop thermal runaway in a battery. So when a battery wants to fail catastrophically, like smoke on a 780 on a Dreamliner, it's because it's gone through thermal runaway, right? So the notion is to use these beads to basically, they break and then they stop the reaction. So the interesting kind of bringing science to application in a very meaningful way. This is a bit of a broader statement about computational chemistry and material science, and I'll transition quickly into materials and electrolytes for batteries. But have people heard about the Materials Genome at all? Is that new to people around here? So the notion of, perhaps I think many people think it's an ill-conceived name, but the notion is, this is a very high-level initiative within the federal government to basically be able to try to start to think about designing materials, basically developing a genome for materials, hard and soft materials. And how does one do that? So thinking about materials that you want to create for a specific function and then design that in the computer. So it's an active program. It's starting to be funded by various federal agencies. And this kind of gets at how one gets to something like the materials genome, at least the path to get there, and some of the potential applications. In battery space, being able to probe a wide range of activity versus potential energy space to hone in on particular catalyst compositions, or how one thinks about lithium peroxide growth in a lithium-air battery. Lithium peroxide's a bad player because it's hard to reverse the reaction, so we have to really understand that very deeply. And so being able to solve that problem in part with computation is very, very important. You all have seen something like this. This is simply my attempt to take the battery problem and overlay it on a multi-scale kind of thinking. But again, this is the way that the folks in the hub, particularly at the other labs and at Argonne, are thinking about how the problems can be solved using a wide range of techniques across the multi-scale space. Ultimately thinking about, could we actually simulate a full battery in a computer? That's actually an interesting challenge. It's not as straightforward as I think you understand that, but a lot of people think, oh, that's probably not that hard. No, it's actually quite difficult. Bringing all the physics and chemistry together is a very, very big challenge. One of the things that we're distinctly doing in the hub is, I mentioned the materials genome. One of the things that is focused on hard materials. One of the things that we brought to the table is, why don't we think about a genome-type approach for soft materials, specifically for the electrolytes? So we're actively going to start to develop a genome project within the hub to explore a wide range of space for soft materials for electrolyte applications, and try to bring that to bear to solve some of our technology challenges with getting to these batteries that I told you that we dream about, these 555. I'll skip through this pretty quick, but again, being able to take this fundamental science and materials science and chemistry and then think about scaling that up, that's a really, really important piece of this. And the labs, we're not the only lab. Oak Ridge has strong capabilities. Sandia has strong capability in this, to be able to take these materials, scale it up, and that's a much better way to have a conversation with industry about how to manufacture this stuff at scale. So this is a wonderful opportunity to actually do, I'll call it experimental validation, if one thinks about using computing to think about advanced manufacturing. What about transportation? A very strong program. This is one example. Susbendu Som's in the room. This is his simulation, so I'll let you talk if they ask any questions. But the interesting thing that we've been able to do, it gets back to what a lab can do. We're able to put folks, computational scientists, who understand combustion and fluid dynamics and all the things that go into it, with combustion chemists, and be able to put together simulations, ultimately imagining that we may be able to design engines from basically to burn anything. Intelligent engine design strategies is what we like to call it. This happens to be a simulation of a single-cylinder diesel engine. You can see it compressing, then expanding, and you're tracking temperature and NOx level as the combustion takes place. But the cool thing is he's also coupling in chemistry here. So being able to think about fundamental quantum chemistry and how quantum effects may actually affect the way you predict engine performance. This happens to be burning diesel, but imagine if you could take an engine and say, I want it to do this, design it in the computer. Then we have test beds like we have test beds in our transportation testing area where we can model, say, we can look at a Caterpillar engine on a test stand and compare that to the simulations. We have shock tubes that do a lot of fundamental combustion chemistry, so a really interesting coupled program that will ultimately, hopefully, allow us to design engines that, say, are 40% more efficient in terms of internal combustion engines. Not as much computing power, but still interesting analysis is, this is a very complicated diagram, but one of the other things that the labs do very effectively, this is an Argonne example, is let's call it systems analysis. Analysis is the energy system, policy to inform policy. This happens to be an analysis that we call well-to-wheels, being able to track energy requirements, greenhouse gas production for production of different kinds of fuels. So the fuels are all arrayed along the left, up and down, from gasoline all the way down to, say, hydrogen-based fuels. The details would be interesting to go through, but the point is we've developed a tool it's called GREET, but it's used by 18,000 folks around the world. But you can actually think about, okay, if I was to do this, if I was to think about what's the value of, say battery electric vehicles in California versus West Virginia versus the US grid mix, or in China for that matter. It's probably obvious to you, but people don't always think about it. If China, for example, is burning tremendous amounts of coal, it doesn't do you a whole lot of good to go to electrification because the source of the coal, from a greenhouse gas perspective, because it's still all coming from coal. So it'll be very different depending upon whether you're in West Virginia or whether you're in California, just based on where the energy is coming from. Interestingly, that makes sense, but these kinds of tools allow us to sort of think about that and provide that information in a very objective, sort of transparent way. You could imagine taking these, and we are doing this, taking some of these kind of tools and pushing them out, say, into agent-based modeling space. And that's where you start to get into really thinking very deeply about how to push this to higher and higher power compute resource. Nuclear energy, I won't dwell on it. We're still playing in all the different aspects of how one enables nuclear energy for the future, everything from safety all the way out to solving the nuclear waste problem. Again, we're still very much on the what's next. What does the next generation nuclear reactor look like? How does one manage waste in a much more safe, secure way? So thinking about those technologies. And really, we spend a lot of time bringing computing together with experiments, small-scale experiment in particular, to try to... And then finally, one example from, again, this is from one of our scientists. This is coming out of the LCF as well. Being able to bring folks who understand the grid system together with applied mathematicians who understand things like stochastic optimization. This happens to be a map of Illinois. All the grid transmission nodes. The color scheme is the price of electricity across the state. And they're actually able to use stochastic optimization. This is actually managed, funded by Oscar, actually, this work. So it's great that Oscar is actually starting to fund work to think about the energy system as well. But the point being that they can start to do what-ifs while dealing with uncertainty, to think about things like, for example, wind penetration. How much could the grid handle 20% wind, which is a goal for the United States by 2020 to have 20% wind? Could the grid handle that? Do you need peaker plants? You can ask a lot of what-if questions, but the beauty of this is, again, you're bringing uncertainty to the table. So it's not just a point analysis. You can really get into much deeper analysis of the grid. So this is work that's actually actively going on. These guys are talking, I know, to the utilities about the tool, and the utilities are excited about it because it really ups their game in terms of being able to think about the grid of the future. So hopefully that gives you a little bit of a sense for some of the things we do. And I think I'm happy to answer questions, but I just wanted to give you a sense of the kind of things that we do at Argonne, the lab strategy, and how we fit in the big picture. So with that, I'll take questions.